Alright, Science, this is Miss Satterley. This is the extra credit opportunity for first quarter. It is designed to where you actually have to watch the video in order to do the assignment. So, I'm going to be performing a few experiments, and you're going to tell me whether or not it's a physical or chemical change, and you're going to support your answer based on what I do. So, let's get started. Okay, experiment 1. I'm going to start off with, I have a container here that has baking soda in it, and I'm going to add vinegar to the baking soda, and we're going to observe the reaction. I'm going to add some food coloring to the baking soda just so it has more of a effect to it. So I'm going to put some green food coloring in the baking soda. I'm also going to do one more thing. It's going to make the reaction a little more drastic. I'm also going to add Dawn dish soap to the reaction. I have my baking soda, I have my food coloring, and a small amount of Dawn dish soap in the baking soda. Now I'm going to add vinegar to the mixture here, and let's see what happens. So in experiment 1, you can see we have bubbles. Bubbles are formed from the release of carbon dioxide. In this reaction, you can see in experiment 1, we have a release of carbon dioxide gas, and we know this because of bubbles. Now, you need to tell me, is this a physical or chemical change? Can I reverse this change? Can I get the vinegar and baking soda back? Or is it a permanent change? The second question that you'll have on your extra credit opportunity is, what is the purpose of the Dawn dish soap? I'm going to tell you though. The Dawn dish soap served as a way to trap the carbon dioxide gas in foam. So when I mix the vinegar and baking soda together and the carbon dioxide is released, it's actually trapped in the soap bubbles. And that's why it was so foamy. I'm going to go ahead and add a little more vinegar, and let's see if we can keep the reaction going and see if it'll go one more time. Oh, well, you can see Satterley got a little carried away, but definitely a lot of carbon dioxide is being released right now in our baking soda and vinegar experiment. So that is experiment number 1. Experiment number 2. I have some corn syrup here, so you can see. I'm going to put some corn syrup into this glass beaker. So as I pour it out, you notice it's very slow. It's a very thick liquid. So I want you to notice the consistency, or scientifically what we're calling viscosity, which is a resistance to flow. We want to see resistance to flow. You can see it's thick and goopy. What I'm going to do now is experiment 2. I'm actually going to take this corn syrup and I'm going to put it onto a hot plate. And we're going to check it and see if the viscosity changes based on heat. Well, you should know this because we did learn this in our physical properties. So I'm going to show you the change in viscosity that we have here. So if I sit here and twirl this a little bit, you can see it's very runny. Now what I want to do is I'm going to pour it into the beaker, or out of the beaker, just so we can observe the viscosity change. So you can see it pours much faster than before. It's actually starting to cool already. So this is experiment 2. What we're going to do with experiment 3 is we're going to actually add water to the vegetable oil. Now, one of the assignments that we had to do actually looked at what happens when you mix water and oil, which I think you guys know what happens, but we're going to show what happens anyway. I have colored my water green, as you can see right here. Okay, and this is just so we can see the difference between the two layers. I'm going to pour it in. So the water and oil are not mixing together. There are some bubbles that are forming, and that's just because the water is being trapped in the oil. But if I let this sit here long enough, all of that will disappear. So again, you can see in this experiment, our water and oil are actually not mixing together, and that's due to the difference in their densities. Water has a density of 1.00 grams per cubic centimeter, while oil is less than 1, and that's why oil will actually float on top of water. So that is experiment 3. Is this a physical or chemical change? Your hint is, what kind of property are we talking about? We're talking about density. Is that a physical property or a chemical property? Experiment number 4. First, I'm going to add some water to my graduated cylinder here. Next, I'm going to add some Alka-Seltzer to my graduated cylinder. We're going to observe and see what happens. I'm going to break it into pieces because it's a little too big. So Alka-Seltzer is used for medication when someone's not feeling well, and that's because there's chemicals inside of it. And you can see it's making me cough. All right. You can see that bubbles are being formed. We know that bubbles represent a certain kind of change. So experiment 4, you have to tell me, is this a physical or chemical change? And what was the evidence for supporting your answer? Now, I'm going to take a minute. I want to mix in experiment 3 and experiment 4 just for an intermediate little activity. In front of me, I have an Elmeyer flask that has oil and water in it. You can see the water has been dyed green, and that is so we can see it. I'm going to take the straw out. So what I'm going to do is I'm actually going to tie in our density experiment with experiment 4, where I use Alka-Seltzer tablets and put it in water. And we want to see what happens. So I'm going to break apart another Alka-Seltzer tab, and I'm going to put it into okay. So what you can notice here is it kind of looks like a lava lamp. This is a chemical lava lamp. So what actually is happening is the Alka-Seltzer is reacting with the water that's at the bottom, but it isn't able to react to oil, and that's because of oil's non-polar properties, which means it's just not going to react. So all of the bubbles that are being formed, they're going up into the oil. When they reach the top, they're releasing the gas and they fall back down. The food coloring is there just for effect, so you can actually see the water going up and down. We'll go ahead and call this experiment 5. We're going to do experiment 6. So first I have some cornstarch here. So you can see I'm going to dump the cornstarch into the container. Cornstarch should look familiar. We just did an experiment with it, so it's a little clumpy and it has an off-white appearance. Next, I'm going to add some water to the cornstarch. I've added water to the cornstarch, and I'm going to try to stir this together. Hopefully, if I get the right ratio of cornstarch to water, we'll get to see what happens. Okay, I haven't done too bad here. So as I start to mix this together, you can see my spoon, I'm having issues with getting the cornstarch to mix together. Oh my, okay. It's all right. This is good. This is very good. Okay. As I'm mixing this together, I have now mixed the water and cornstarch together. I'm going to show you a couple things. I'm going to very gently run my spoon through the liquid. So it seems liquidy. If I try to move it through force, I'm having much difficulty with this. So if I apply pressure, you can notice that it almost looks like the consistency of it is changing. Again, I'm going to go soft. As I slowly stir it together, you can see it's letting me stir. But if I go forcefully, I'm having issues here. I can almost cause there to be an opening at the bottom. Oh, that was a nice effect. So as I start to stir this, you can see I'm being very forceful with it, and then all of a sudden I let go and it looks like a liquid again. Cornstarch, when it's mixed with water, its viscosity is actually based on pressure, not heat. So corn syrup was based on heat. Cornstarch is based on pressure. This is because cornstarch is what we call a non-Newtonian fluid. So I could actually pick this up in my hand, and as long as I was applying pressure to it, I would have a solid ball. Experiment 7, I'm going to use the cornstarch here. I actually have some iodine that fell before I wanted it to. And I'm going to add just a little bit of iodine to this. And I poured way too much, but that's okay. You can see, mix this together. It's very black color, but against the cornstarch, you can see that it is a purplish color. This is a chemical reaction. Just give you the answer again. And this is an irreversible color change. I cannot get this iodine color back. So I just wanted to let you guys see it a little more larger scale so you can see the purple tint that comes out. Next one, experiment 8. I'm actually going to take some regular table sugar and I'm going to put it on heat. We're going to see what happens. And this is what happens. So this, at one point, looked like this. You can see there's a big difference between the two. This is very hot. I actually let this sit a few seconds too long and I burnt it, but that's okay. What I've actually have done here is I've created caramel. So caramel is just sugar that has been cooked or heated. The heat is causing a chemical reaction to happen. So this is an irreversible change. Now this caramel in particular probably wouldn't taste very good, but if you've ever had it in candy, it's quite delicious, and that's actually just sugar that has been cooked. So ours is a little darker here. You can still see kind of a caramel color. So that's experiment 8, cooking sugar to form caramel. Next one is experiment 9. In our container here, we have some melted magnesia. It's commonly called Malox. It is a medication that can help with acid reflux or upset stomach. The second thing that I have is called phenolphthalein. Go ahead and show you here phenolphthalein. I want to focus on the color of the phenolphthalein. It's a clear liquid. So this is a clear liquid, and this is a white liquid. I'm going to mix these together. We're going to see what happens. Make sure you're watching. So what I've done here is I've added something called phenolphthalein. Phenolphthalein is a type of acid-base indicator. It is a type of chemical that helps determine the pH. It actually turns a bright magenta color when it comes in contact with a base. Milk of magnesia is basic. The question is this a physical or chemical change? I'm going to add one more thing to our solution here. Vinegar. Vinegar is actually acetic acid, which is a type of acid. What are you noticing when I pour the vinegar into the milk of magnesia and phenolphthalein mixture? You can see it turns back white. That's because vinegar is an acid, so it's changing the pH. If I let it sit or give it another stir, it's going to go back to pink. Now, if I add enough vinegar, eventually it will stay white. Is this a physical or chemical change? So we learned that chemical changes have irreversible color changes, but I have just actually caused the pink to go away. So you need to think about that when you answer your question. For experiment 10, I'm going to use a very small amount of ammonia. I don't want to use a lot, so we're going to do this. This would be considered a micro experiment, so a very small quantity. I'm also going to mix copper sulfate. So if you see, copper sulfate is blue. In one of the PowerPoints, I do stress that anytime copper is in a compound, it's always blue. Ammonia, you can see, is clear. A small amount of ammonia that is in the container here. And now I'm going to add a little bit of copper sulfate, which is light blue, and we'll see what happens. So you can see when I mix the two together, there is a dark blue color that formed. But then, as I stir it, and you can see there's actually a light blue precipitate that forms. So as I move it back and forth, you can see the little light blue crystals. So we had two different liquids that were completely liquid, and now you can see there's a precipitate that's formed when we mix these two compounds together. And that is experiment 10, and that will be it for the extra credit assignment. If you have any questions, please let me know. Bye.